My name's Violet Eagle. I'm a master's student at NDSU in the Soil Reclamation Lab. I'll be giving most of the presentation. I'm here to present my research on the response of plants to soil compaction and soil water content. I just want to apologize. I'm still running the data on the One Oak pipeline soils textures and stuff. So I don't actually have that data ready. So I'll give a brief overview. The first couple slides will be the justifications for my research, and then the next couple slides will go through methods. I have about 6 results and 2 conclusion slides. So we're going to start with I borrowed this graph from Justin Kringstead, who presented yesterday. This is the North Dakota pipeline construction. What's circled there is the total miles of pipeline currently in North Dakota. So if we take that number and we multiply by the average pipeline right of way, which is about 100 feet, then we get this number, which is 376,000 acres of disturbed soil. We've had a couple of people talk about how important it is to look at this soil disturbance that's happening with these pipelines. So first, we're going to define the specifics of how pipeline installation relates to soil disturbance. So as Amanda said before, first we've got to scrape that topsoil. We got to install the pipeline that's there, and then you replace the topsoil. And this middle picture here is to just really demonstrate how at each one of those steps, you're going to have these really big machines in there. You have different times of the year where you have to be doing these things. You can have different water content, like right there we have snow on the ground, but here it's very dry. And all of those are going to affect how what that soil compaction is going to look like. So we've had several people in this conference state how important it is to look at soil compaction and how compaction can happen at these pipeline installation sites. So let's get into soil compaction. It's defined as a general hardening of soils, and it's controlled actually by these three factors interacting. First, we have texture, which is the particle size. That's your sands versus your clays. We've got water content, which for us will be defined in field capacity. So field capacity is the amount of water held in soil after excess has drained away. Different soils will have different water as field capacity. So that's important to note. Finally, we have the bulk density, which is what most of us think of as compaction. That's the weight per a given volume. For us, that's going to be grams by centimeters cubed. Compaction is a general hardening, but what a plant might feel is something called penetration resistance. And that's going to change with each of those different factors. How plants behave in the face of compacted soils is variable. Here is actually a diagram we have adapted from Brady and Weil. That's like the main textbook of soils. And what we have here is bulk density. We have a general rule of thumb that if that bulk density reaches 1.7 grams per centimeter cubed, that's when a lot of researchers noticed that root penetration begins to be inhibited. However, different plants are going to have different root behavior. Some plants are just generally going to have more aggressive roots, or just have the ability to penetrate that bulk density a little better. Different soil textures, obviously, are going to behave differently in terms of that bulk density. Some soils are just going to be a little heavier, so that bulk density doesn't necessarily mean the same thing. And water content. So water content is very important for these roots because it can act as a bit of a lubrication for increased bulk densities. So in terms of compaction remediation, the picture we have right here is of an alfalfa root. You can see that it met a compacted layer and it just started growing sideways. Compaction can remain inhibited for years, and it's very variable. I've seen cases in the literature where 2 years they just seeded it. They didn't do any remediation, like physical remediation, and it was totally fine after 2 years. I've seen one case where it was 40 years, they were still seeing a very compacted layer that inhibited roots. So the only surefire way so far the literature has encountered to combat this compaction, to remediate this compaction, is by deep ripping, which is tilling deeply, basically. However, this can increase your soil erosion. This can open up your soil to invasive species. But most importantly, it's very expensive and super difficult, particularly if you're talking about an installed pipeline. So we'll start off with my objectives for this. We've got first to evaluate the influence of bulk density and water content combinations on that soil penetration resistance before and after plant growth in 2 different soil textures. And then secondly, it's to evaluate or monitor the influence of the differential rooting environments on the plants above and below ground. So in order to do this, we chose 2 plants. We've got our western wheatgrass, which is a native perennial grass, and we chose oats, which is a common cover crop. It's not uncommon to see either one of these in a remediation seeding mix. Mostly just for time and consistency, we limited it to these 2 plants. So for each plant, the western wheatgrass and the oat, we've had 2 soil textures, bowbells, which is a loam, and flasher, which is a sandy loam. We used aluminum rings, commonly used in bulk density measurements. We wetted our soils up to different percentages of field capacity, and then compaction was achieved using a hydraulic press, as shown in the picture. We added different amounts of soil in order to achieve different bulk densities as well. They were seeded and incubated, and then they spent 14 days in a growth chamber. So each one of those, sorry, this gets a little difficult. Each one of those soils, for one soil texture, we had 3 different levels of water content based on our percentages of field capacity. And we had 3 different bulk densities. We had a high, a medium, a low, and a wet, a damp, and a dry. Those created these 9 groupings. and each grouping was replicated 3 times. So after a total 21-day growth period, above ground biomass was separated, like in the picture. Penetration resistance was measured with our Humboldt penetrometer, and then the roots were washed and measured with a wind rhizo machine for total length. And so we'll start off with the results, the oat results for this penetration resistance. Some important things to note is that this is, sorry, so our x-axis, these are the bulk density groups. Each figure corresponds with one of the soil types, and they are grouped by water content. So as we can see, this flasher, our sandy texture, much more muted response than our loam texture, not super surprising in terms of penetration resistance. And this is for the oats. This y-axis is our is in megapascals, which it's important to note that about 2.5 is concrete. Like that's the same. For our Western wheat results, we've got our bulk density, our water content groupings, our bow bells versus our flasher. I want to point out that this megapascals scale is the same as the last graph. So we can see that this Western wheat results are more muted, but they have that same trend where it's the flasher has less of a sort of more muted response to the penetration resistance. We'll move on to above ground biomass. This is for the oats. Our X and our groupings will stay the same. However, our Y-axis is now biomass in grams, and that was dried down. And in the oats, I think it's important to note that this water content suddenly becomes very much more important, where each of these groups is more related to the water content than it is to the bulk density. So even at this higher bulk density, we can see that this higher water content, we've still got above ground biomass being established. And here is the Western wheat results. Unlike in the penetration resistance, I had to change the scale of this y-axis because the Western wheat above ground biomass was so much finer than the oat biomass. But we can once again see that it is highly correlated with those water content groupings, more so than the bulk density. And then finally, our root lengths, same x-axis, same water content. This is going to be root length in centimeters. And in this one, we can see that once again, that root length is very highly correlated with that water content, particularly in our flasher, which is our coarser texture soil. And much like in the above ground biomass results, I had to change the scaling of this root length because in the oats, we can see that we get a lot of length on these roots. But in this one, we got much less length in the roots. This is not surprising given that Western wheat is a perennial, but I'm going to talk about that in the next slide. I'm sorry. And we did see these general trends where bulk density is starting to affect or looks like it's starting to affect the total root length. But obviously we can see that water content is a little bit more important than the bulk density. So I wanted to show just a comparison. This is after the 21-day growth period. These are the oats. That's what an average oat looked like. That is a lot of roots. That's an insane amount of roots. And our Western wheatgrass, it's not terrible, but it's just got like a smaller system. So it's in our conclusions where the most important thing to point out is that perennial growth in general, which is what Western wheatgrass is going to be slower. And perhaps it's that our 21-day growth period was just a little too not long enough for it. In terms of what this means for reseeding pipelines, companion or cover crops can be considered due to that fast initial growth of those. Sorry, it was really important, but water was the most critical to successful vegetation in this laboratory setting. So that's helpful to know that while texture and other things can be super variable, maintaining effective water management can really help increase that plant establishment, which then mitigates compaction restraints, offering an approach to improve soil structure and plant productivity. And that's our big picture. That's one of the pipelines that Amanda was talking about as well. That was a soil sampling. I want to thank OneOak and Soil Reclamation Laboratory, as well as NDSU. Thank you for having me.